Welcome to Sundar's lecture. This is lecture number 84 and in that it is A. See, in this lecture we are going to see steady state analysis of coupled coils, right? What is steady state analysis of coupled coil? See, if you have a circuit like this, like RL or RC, anything it may be, you close this circuit and you leave this circuit for some time, because transient analysis is different from the steady state analysis. Yeah, if it is a transient analysis, we would have done this before, right? In my previous classes, maybe transient responses of RLC circuit, there we would have studied what is the transient responses for RL, RC and RC circuits. And now we will see a steady state analysis of the coupled coils. What is steady state analysis? If I close this particular voltage and leave the circuit for some time, let it come to the steady state, and then we need to analyze this particular circuit, right? So what are the topics we have seen? See, we have taken some problems in the previous class, and we have solved it, right? Now in this class we will do some more problems, and before that we need to compare two expressions. See, if this is the first circuit, and how will you write the expression? Right, if you are writing the KVL expression, what is the equation here? It is plus V of t, because I am going from, my current is like this, so I am going from minus to plus. It is plus V of t minus I into R, and this current is coming like this, so it will be minus L into di by dt, right? L into, because there is no coupled coils here, only one inductor is here, and that is the value of this particular coil inductance is L. No mutual inductance, because no another coil is connected. So this will be is equal to 0. Maybe this is the first expression. Maybe if you come here, you know this one, right? You can convert this L value into XL if they have given you with omega, that is 2 pi, you know, constant, F value for frequency value, and you write the expression for this particular circuit. See, it is the current is traveling from minus to plus, so it is V of S minus I into R, and then this current is coming here, so minus j omega L into this current is I, right? So I, which is equal to 0. See, make this as expression number 1 and make this as expression number 2, and you compare 1 and 2 now. Compare expression 1 and then expression 2. See, everything is same, right? This is V of S and this is V of T. I into R, I into R, I into R, I into R, minus, everything is same. See here also you have L, here also you have I, here also L, you have I. So the term d by dt, this operator d by dt, can be replaced with j omega. That is the point I need to conclude. So the term or the operator d by dt can be equalized to j omega. Try to understand. This is very important to understand, right? So this is actually in time domain and this is actually in the frequency domain. So d by dt will be equivalent to j omega. You try to understand this. This is very basic thing, and we will take a problem now. See what is they have given you. See, it is very there is an, you have to be very concentrated to understand these kind of problems. Please be with me, otherwise you will not understand these kind of problems, right? We need to find the current I1 and I2, and they have given you the circuits like this, and they have given you the circuit, and this is I1, this is I2, everything they have given you. See, very simply, so you see here, this is I1, right? So what is the current here? It is I1, this is I1, and this is now I2, right? This is now I2, and we know that one. So if that is so, what is this current? Simply it is coming in, it is going away. If this is the direction, then obviously it will be I1 minus I2. See, these kind of basics I am not doing it for you, because you know, you apply KCL here, you make it as X now, and this current will be obviously I1 minus I2. You know these kind of things, right? So what is the other thing? Now I need to write the KVL expression for this particular loop, right? So KVL for for loop number 1. Loop number 1. What will you get for the loop number 1? See, this current is in this direction, so I will go fast because you know these kind of things. It is 5 at a 90 degree. What is 5 at an angle of 90 degree? It is 5j, right? So minus 2 plus I am traveling, so it will be 5j, and I am going in this way. See this one. This coil has mutual inductance to this particular coil, right? What is the value of that mutual inductance? They have given you directly in ohms. So it is the reactance value. Try to understand. This is the reactance value. So whatever we have seen in this particular topic, you see, you can replace, right? You don't need to put L into di by dt. No. If they have given you with the reactance, you can straight away write the value. See, I will write it down. So now you see, this current is entering here. Anyhow, I am going to write for the self-induced EMF. So if it is self-induced EMF, I have already told you, don't do anything, put plus, and what is the current entering in this coil now? It is I1, minus I2 multiplication of 2j, that is self-induced EMF, right? And now I have to see for the mutually induced EMF. Try to understand very clearly. You just concentrate and just follow me. See this current. I'm seeing this current, right? This current is actually leaving the dot. Here it is dot, so it is not entering. It is actually leaving, right? For this particular first coil. And what happens in the second coil? This is current I2, right? This is current I2. So you see here, this I2 in this coil, it is entering. Here this current is leaving. Here this current is entering. Try to understand. So what I have to put here? I have to put minus because the current is leaving here. The current is entering here. And what you have to write? The second coil's current and multiplication of this mutual reactance. So it is 4j I2. 4j I2, right? That's all we have written, right? That's all we have written. So no other components are connected, so which is equal to 0. And this is the equation. Try to understand. I will repeat it again. See, I have to write the KVL expression for this particular first loop, and I am starting from this point. So I am traveling from minus to plus. This current is traveling from minus to plus. So 5 at an angle of 90 degree can be written as 5j. So plus 5j. No. I made a mistake. Right? So I made a mistake. This one, this whole term, this whole term, this whole term, this one, 5j, that is equal to here itself it will come, right? So you will have this expression now, right? That's all, right? So 5j, and which is equal to this will not come down. So which is equal to, you see here, it is I1 minus I2 into 2j. Why it is I1? Directly you have to put plus values for the self-induced EMF. I have told you already. You don't put minus for the self-induced EMF. I have just taken this current and the 2j, that is this coil's reactance, and I have directly put this value. And I have to see what happens to current in both coils to write the mutually induced EMF. This current is leaving dot, this current is entering dot. So the minus will come here, and this value is 4j, and what is the current flowing in the second coil? It is 2j. It is I2. Then I can write like this. So this is maybe if I further simplify this 5j, maybe I will directly write down the expression. And if I simplify this, you just simplify yourself because I don't have time to simplify these kind of things. So I will get an expression like this. You just put multiply and then you bring the constant terms to the other side and I1, I2 to the other side. So you will get expression like this. So this is the first loop expression, and we will go for the KVL for loop number 2. See, it is very important to understand one thing here, because why I am telling you, you have to take a current differently, because you see here, this current is I1 and this current is I2, right? I2. See here, I have made a mistake. This one. this current. See here, this current is I1 and this current is I2, right? And if you draw the current here, why I am doing this? Because this will help you. See, try to understand. I can write the expression with this current itself, but this is my way of looking into the circuit, because it is very easy, because you write this current now. This is I2 minus I1. Simply, if I take like this current will be, you put KCL, apply KCL, and you write this expression, you will get this one. See, try to understand. I'm not writing with this current. I always do this one. So you please do this one, right? So what will be the equation now? So this loop equation I have to write. So I have to write the voltage equation for both this coil. So I will first write this coil's voltage, right? So for the there is no voltage sources, right? There is no voltage sources. So it will be 0, no voltage sources. That will be is equal to, if there is a voltage source, then put that one, and then equal to, you write the voltage equation for the coils or resistance, whatever it means, whatever the circuit is connected with, right? So it is 0 now, and then you start with this coil, and then you go for this coil also. See, this coil, what is the self-induced EMF? This current is coming in any direction. The value will be in plus, so it will be 3JI2. That is self-induced EMF, right? Self-induced EMF, right? It is I into XL. What is I into XL? It is obviously voltage, right? Anyhow, self-induced EMF. And I need to go for the mutually induced EMF now. See this one. This coil's current is I2. That is entering through dot. Entering through dot. And you come here. This, I have to see this current. No, you should not see this current. Forget about this current now, right? So I have to see this current now. And this current is also entering through that. So what I have to do here, I have to put plus, and then it is I1 minus I2, that is current in the opposite coil. And what is the mutually coupled or mutual reactance? That is 4J. That is 4J. So this is self-induced EMF, and this is mutually induced EMF for this particular 3J coil. 3J ohms coil, anyhow, right? So the next one, I have to see for this coil now. For this coil, see this current. I don't need to see anything. Directly you put plus, because I am writing the self-induced EMF, and you will get I2. Sorry, this one I have written I1 minus I2. Oh. This one, this one, this one. It is not I1 minus I2. It is I2 minus I1, right? It is I2 minus I1, right? This current. Now you come here. This coil self-induced EMF, it is I2 minus I1, whatever it may be, whatever the dot convolution, whatever dot you have. If you are writing for self-induced EMF, don't put minus, directly put plus. And what is this value? This will be 2G. This is what? This is the self-induced EMF for this 2J ohms, right? And then you go for the mutually induced EMF now. And it is very simple. This current is entering through that. This current is also entering through that. So you have to put plus. And what is the other coil's current? It is I2. And what is the self-induced, mutually coupled reactance? That is 4J. So what you will have plus 4J I2. Right? This is nothing but the value of mutually induced EMF for the second, for this particular 2J coil. So we have written the expression, right? So if you further simplify this, so I am getting it to be 6J I1 is equal to 13J I2. So I have simplified. So please you do by yourself, right? So if I further write this one, so I can write I1, which is equal to I1. If I am writing I1, so it will be 13 divided by 6 I2, right? 13 divided by 6 I2, and make this expression to be number 2. Try to understand. Just JJ will be cancelled out because this is 0, so you will get this expression. So what you do now, substitute expression number 2 in expression number 1. What will you get? So I will substitute this values now. So it is 2J. What is the value of I1? I can put like this, right? So 13 by 6 I2, 13 by 6 I2 minus of 6J I2, minus of 6J I2, that is equal to 5J, right? That is equal to 5J. And if you simplify, see, only I2 is the term, right? Only I2 is the term, and you can easily get the values of I2, right? If I simplify this, I will get I2 as and you see I am getting I2, directly I am just writing the values. I2 will be is equal to minus 2.976 amperes, 976 amperes. That is the value of I2, and you just substitute I2 in expression number 2, right? In 2, what you will get? You can directly get the I1 value. What is the I1 I am getting? It is minus 6.45, minus 6.45 amperes. See, try to understand. If you write the KVL expression for both loops, it will be very easy. Very easy. It is like a circuit. It's like circuits problem. But anyhow, you have to understand the procedure of writing the KVL expressions if you have dot convoluted coils, dot convolution coils, right? So this is how. So I'm not putting or I'm not solving the basic algebraic equation. See, please, you do by yourself, right? Then I will give you the idea about how to write the expressions, right? You'll go to the next problem now. Next problem. This is also the same thing. You have to understand. See, this is the problem. You have to find what is the value of I1 and I2. I will go very fast now. So KVL for loop number 1, for loop number 1. So what is the value? You have 100 volt, right? So directly you put 100, which is equal to, see, for these kind of things, it is very simple. You can directly put the values because this I1 is traveling like this. So what you will get if you put equal to symbol? So it will be 4I1 minus, it is already minus is here, minus 3J I1 minus 3J I1. See, I have to see this current. What is this current? I have already told you. What is this current? Simply, if you put KCL, apply KCL, you will get I1 minus I2, right? You know this one. And then you see, if I am going for self-induced EMF, put plus, it is I1 minus I2, I1 minus I2 into 6J, That is self-induced EMF. And if you are going for mutually induced EMF, see, this current is I2, right? This current is I2. You know this one. And you see, this current is entering through dot. This current is leaving the dot. This current is leaving the dot. So what you have to put here? You have to put minus I2 into this, this mutually coupled reactance. So it will be 6J, not 6J. Mutually coupled reactance, it is 2J. And current in the second coil, it is I2. Why I am putting minus? Because current is entering through dot, current is leaving through dot in this coil. So now that's all, right? I have completed, which is equal to 0, right? So now not 0. I have written this one. So I have written for this one, and this one, right? So completed. The equation is completed. So if I simplify this equation, what I will get? So I am getting it to be 4 plus 3J I1 minus 8J I2 is equal to 100. See, I'm repeatedly telling you, please, you just solve these kind of things. I'm not doing it because of the time. I don't have time for these kind of things. Right. Anyhow, now I will go for KVL at loop 2. Loop 2. See here, is there any voltage sources available? No, right? So what you don't need to do, you don't need to write any voltage source because it is 0. That is equal to, see, I will write first for this particular coil. What you will get? Maybe for this one, you have to write this current, right? This current. So this is I1, and for this is I2, and if I write this current will be I2 minus I1. I should not see this current now. I have already told you, don't see this current. And now you write the expression self-induced EMF. What is the self-induced EMF? It is 8J I2. Straight away I will put plus values. And then you see this current is entering through dot, leaving the dot here. And see this one. You have to see this current, not this current. So this current is also leaving the dot. If it is going like this current is leaving the dot, this current is leaving the dot. So I have to put plus. What is the mutually coupled reactance? It is 2J. What is the current entering this coil? I'm just writing the expression, voltage expression for this coil. So what is the current entering this coil? It is I2 minus I1. So this is self-induced EMF. This is mutually induced EMF for this particular coil. And then this value, it is very simple, plus 5 I2 plus 5 I2. It will be like this. That's all. Now you have to see, you have to write the expression for this particular coil. So you come here, whatever it may be, you put plus, because I am writing the self-induced EMF, the current is I2 minus I1 multiplication of this 6J, There is no issues with that. Now you have to see, you have to write the mutual induced EMF because these two coils are mutually coupled. So this one you see, the current is leaving dot, this current is also leaving dot. So what I have to put? I have to put plus this value, mutually coupled reactance, that is 2J. What is the current in this coil? It is I2. That's all. See, I have written voltage equation for this coil, self-induced EMF. This is self-induced, this is mutual induced, and this one is simple. It is like voltage, right? For this coil, this is self-induced EMF, this is mutual induced EMF, right? Once I've written everything, right? So if you further simplify this, I will directly write the equation, and I am getting it to be I1 which is equal to 2.25 minus 0.625 J into I2. Make this as expression number 2. And it is very simple now. Substitute expression number 2 in expression number 1. So if you do so, I have to substitute I1, right? So it is 4 plus 3J. Multiplication of 2.25. This I1, I'm just putting it here. So 2.25 minus 0.625 J into I2. I have substituted, and then minus 8J I2, which is equal to 100. See this one now, everything is I2. Simply, what you do? You just find what is the value of I2 straight away. You can find what is the value of I2, and I am getting I2 as 8.218 plus 2.833 J amperes. That's all. Now substitute I2 in expression number 2. You substitute this one here, multiply these two, and you will get I1. I am getting I1 to be 20.26 and then plus 1.238 J amperes. That's all. That is what they have asked you to find I1 and I2. See, I have told you, right? If you write the KVL expression, then these simplifications are very easy. Algebraic simplifications, right? So we will go to the next problem now, and this is the next problem. Again, you see, I will write it down. What is the current here? Straight away, you just, because we have practiced well now. This is I1 minus I2. For writing this loop, I have to see this current. And what is this current? This is nothing but I2 minus I1. I have to see what this current, only writing the expression under this loop, right? Now you straight away write the expressions, right? Don't waste our time. So we have a voltage source. So it is 5J. Straight away, which is equal to, and this value will be 3I1, and you see, I have missed this one, right? Because this is coupled coil. Anyhow, I will put the values. This is 3J. That is a mutual coupling. It is 3J ohms. Anyhow, see, now I have to see this current is entering through that, right? This is I1. I know this kind of things. So this is I1. So this is if I want to write what is the self-induced EMF, I have to put plus 4J straight away. It is I1, right? I1. Now I have to see the mutually. I have to write the mutually induced EMF. So you see, the current is entering through that here. The current is also entering through that here. So it will be plus, what is the current entering in the other coil? It is I1 minus I2 multiplication of this value, 3J. That's all. I have written self-induced EMF, I have written mutual induced EMF. Now I have to come to this coil. Straight away I put plus I1 minus I2 multiplication of 5J. This is self-induced EMF. See, try to understand, while writing self-induced EMF, whatever it may be, you put plus. Simply you put plus, right? Now I have to see the mutual induced EMF. This current is entering through that. This current is also entering through that. What I have to put here? Plus. And what is the other coil's current and the mutual reactance? That is 3J multiplication of I1. I1 simply, right? So I have written, right, everything. So nothing is connected again. So this one I have written, this one self-induced EMF, mutual induced EMF. For this is self-induced EMF, this is mutual induced EMF. So I have written. So if I simplify this, what I will get, so if I simplify this one, I am getting it to be 3 plus 15j into I1 minus 8j into I2 is equal to 5j. Simple. You don't need to panic very much, because you simplify this, you will get this expression. Now I will write the expression for this KVL loop. So I have to see this current, not this current. See, try to understand, right? So if I write so, what I will get? So there is no voltage sources. So straight away put 0 equal to. See, this is very simple, right? Because this is capacitance. So it is minus 8 j into I2 straight away into I2, because that is minus here. And then you come here, if I want to write what is the self-induced EMF, straight away put plus, and this value it is I2 minus I1 multiplication of this 5j. This is self-induced EMF, right? Now I have to see the mutual induced EMF. See, this current is leaving dot. So don't see this current. This current is leaving dot, but this current is entering through dot. So what I have to put here? You have to put minus and multiplication of this current, opposite side coils current, and the mutually coupled reactance, this value. So if I further simplify this is the equation, that's all right, I have written. So if I further simplify this, and I am getting, maybe I will write it down. Say I am getting it to be I2, straight away I will write I2, which is equal to minus 8 by 3 I1. Minus 8 by 3 I1. This is expression number 2. And you put 2 in 1. Simply, you put 2 in 1. Straight away substitute I2. Instead of I2, you substitute the values. What you will get? So 3 plus 15j into I1, this value, and minus 8j, and minus 8j, instead of I2, you substitute this value. Minus 8 divided by 3 into I1, which is equal to 5j. And you do so, you just simplify this, everything is I1, right? So for I1, I am getting the value of I1, it is 0.137 plus 0.011 j amperes. This is I1, and substitute same thing I1 in expression number 2. So you substitute here, you will straight away get what is the value of I2, and I am getting the value of I2 to be minus 0.367 minus 0.029 amperes, J amperes. See, I have found what is I1 and I2, but what is the question they have asked you? They are asking you to find what is the voltage across this 5 ohms resistor. What will be the 5 ohms resistor's voltage? This is nothing but maybe 5 ohms means this value, this not resistor, this is reactance. I have made a mistake. I have changed this one. 5 ohms reactance means I need to find what is the current in this particular resistor in reactance. So what was not current, the value of voltage. So what is the voltage expression? You take this one or this one, anything it is correct, no problem, whatever it may be. See, if I want to write what is V across 5j ohms, simply you write this expression, what is the voltage, write the self-induced EMF with this current. It is I2 minus I1 multiplication of 5j. This is self-induced EMF. And then you see this current is leaving the dot. This current is entering the dot. So what I have to put here? I have to put minus this current I1. Multiplication of this 3j. Simply that is the voltage across this. Or you use this I1 minus I2. Anything you follow, you will get the same answers, right? So you substitute I2, I1 and this I1, and finally if you substitute, you have all the values with you. So 5j ohms will be is equal to, if you substitute and simplify, and the value I am getting it to be minus 0.23 plus 2.93 j, right? This is the final expression. This is the final expression I am getting. Okay, fine. We have completed, right? See, I don't have time for other problems. Maybe I planned to have only one lecture for solving the problems in dot convolution. or coupled coils, steady state analysis in the part of steady state analysis. We will go for the another one lecture because I need to solve more problems to give you good clarity. Please bear me. I have taken other two problems. See here, I have another problem and I have another problem too. So let me give time for another lecture and we will see in the next one, right? So what are the topics we have seen? Only three problems. See, the main idea, the main idea we have taken for the steady state analysis of a coupled coil, and if I write the expression for this particular time domain and for the frequency domain, if it is given with the Excel values, and I can easily compare that d by dt operator can be replaced with the j omega terms. That is what we have compared, and you see we have taken the problems with the j omega l terms, right? And we have planned how to write the expressions for mutually coupled coils. That means exactly how to write the self-induced EMF and mutually induced EMF. See, very clearly you have to understand. If you are writing self-induced EMF, straight away put the plus. Straight away it is the positive value. And if you are going for the mutually induced EMF in a particular coil, then you see whether current is entering in one coil in the other coil. You have to compare two coils. You have to compare two coils current. And if both coils current are entering through that, then put plus. If both the coils have different current directions, you put minus. That's all. Very simply. Students will do mistakes while writing the mutually coupled, mutually induced EMF. This they will write this value instead of this value. Right to understand. You have to be very careful writing this expressions, right? So we have seen problem number one. We found what is I1 and I2, and again we have taken some more complicated with to find I1 and I2, and now finally we found what is the value of voltage across the 5 ohms reactance, right? Then we will see in the next class. Thank you.